So, still looking at permutations now. We're looking at what we call like objects. Now, you might have been, or you may not have, but in the previous lesson when I grouped those books, the Chem, Physics and Bio, you might have kind of thought, are they the same? Well, maybe they are, maybe they aren't. So that's one of the subtle things you got when you read the questions. So if they're talking about like objects, then those things are identical. So the 4 physics books, they may have been identical, but you could have 4 different physics books there. And so in this particular lesson, what we're going to be looking at is when the things are identical. So here we are, we're looking at word bookkeeper, for example, and so as it says there, let's swap this E and that E, let's swap them around. So if I swap them around, so book K, so I've left that there, but now I'm putting this E here, that E and that P are staying, and this E, that's what I'm putting that there, if I've swapped them, and there we are, bookkeeper. Now, to me, those two, bookkeeper work, they look exactly the same. So because like objects, the E's are the same, so like objects, identical. All right, and you need the word identical or some other, go and look it up in the thesaurus word, that needs to be in the question for you to know that they're exactly the same. All right, so we need to take into account how many ways the E's can be. We've done it there, isn't that nice? We need to take into account how many ways the E's would be arranged. So, which would be 3 factorial ways. So, in the word bookkeeper, there are, what is there? There's 10 letters. All right, so there's 10 letters in that group, We've got, already said, we've got 3 E's, we've got 2 K's, we've got 2 O's, and 1 of everything else. So our number of permutations, let's see what I've got there. So my number of permutations or arrangements then would be the number of ways my 10 could be arranged, which would be, so the number of arrangements, let me go back. So the number of different arrangements. All right, because that was up higher, that was an arrangement, but they weren't different. They looked the same when we swapped those over. So it'd be 10 factorial, but then we've counted 3 factorial ways in that 10 that the E's could be swapped amongst themselves. And remember, it doesn't look any different. So we need to then divide by the 3 factorial. Because there's 2 K's, we need to divide by that as well. And because there's 2 O's, we need to divide by 2 factorial. And that's a calculated job. And when you do that, you get 151,200 arrangements of those 10 letters that actually look different to each other. All right, so in general, the number of permutations of n objects where n1 are alike, n2 are alike, and so on, is that what I've just done there. So it's the total number divided by the different ways you could arrange those things amongst themselves. So here we've got notice the word identical. So 5 identical knives. So that means when I take this knife and I swap them around, it still looks exactly the same. Okay? And so the word identical is the key word there. So what have we got? We've got 5 identical knives, 6 identical spoons, 8 identical forks in the drawer. How many ways could we take them out and line them up? Probably should have different ways. All right, that's kind of what I'm probably too lazy to write that, but anyway. So how many different ways? Well, 5 plus 6 plus 8 is 19. So we got 19 objects. So our number of ways would be 19 factorial, but then we have to take into account the 5 knives. When you swap them around, doesn't make it look any different. So 5 factorial. Same with the 6 spoons. When you put them around, doesn't make it look any different. Same with the 8 spoons. When you swap them around, doesn't make it look any different. All right, that's calculator job. So get your calculator out. You can use your calculator. You can use the fraction template to come up with fractions and let your calculator do it all. And when you get that, there's 34,918,884 different ways that we could arrange all of those objects. Right. Here's another way that we can apply that thing. So the grid below shows 2 points A and B. You can travel from A to B by going only right or down. All right, so I can go from here to there. I can keep going right, I can keep going down. But if I'm here, I can't go that way. I can't go left, I can't go back up. All right, so I can only move right or I can only move down. So to get from A to B then, if I can only move right and down, I've got to go across 1, 2, 3, 4, I've got to go 5 lots to the right and 4 lots down. All right, so I need to travel, I need to travel 5 to the right and 4 down for a total of 9. All right, got to change total of 9. All right, so my number of waves then would be my 9 factorial over 5 factorial for the number of different ways of being right and 4 factorial for the number of ways of going down. Effectively what that's saying is going there and there, there and there, no different to each other. It's exactly the same because you end up here at this spot. All right. And so when you get out your calculator and do that, you'll find out there's 126 different ways that you can, pathways that you can actually go on to do that. All right, so let's see how you go with all of that. That's the last of the permutation stuff. And remember that permutations are arrangements, different ways we can arrange things, and that the order is important. And then of course in this last bit, if you've got things that are identical, then swapping the order doesn't make our arrangement look any different. All right, as always, have fun.